All right, so Joris is gonna.
Sorry for the delay. To go. So I'm going to talk about Dask, a way to work with Python, but in more parallel and distributed ways. But first, small intro for those who are not really aware of the Python ecosystem or scientific software and data tools. So it's a very rich ecosystem. One of the foundational libraries, NumPy, for the providing the numerical base to do numerical computing in Python. A lot of other libraries building on top of this core. You have the plotting libraries, the typical scientific routines, symbolic computing, pandas for more the data analysis, and also on top of this base, you have a lot of packages, a rich ecosystem. Small, in more detail about pandas, because I'm going to mention that a bit more. Maybe just to get an idea, who knows pandas? Quite some. Who uses pandas? Quite some. Okay, so maybe also to clarify, I'm a core developer of pandas, not of Dask. The thing that I'm presenting today is just something that I used a little bit and I find a very useful tool. Pandas provides, for those who don't know it, very high performance, easy to use data structures in Python. It's typically used for tabular data, spreadsheet-like data. So not if your images or large arrays, but for structured tabular data. You can read and write a lot of data files. You can easily do a lot of computations, group by operations, and things like that. I'm going into detail into that. So there is a very rich ecosystem, data science ecosystem in Python. There are only some problems with that. Most of the libraries I showed, not all of them, but most of them are restricted to in-memory data, to single thread, single cores computing. For example, pandas. You can work with pandas, with large pandas data frames very easily, as long as your data frame fits into memory and best fits. You have quite some memory. So that's a problem if you want to keep on using your familiar NumPy pandas data tools, scikit-learn data tools, for example, as well. But your data set grows, you get bigger data, or you want to parallelize your data flows. So that's where Dask comes in. So it's a flexible library for parallelism. What is it exactly? So it tries to do parallel computing, which lets you work on data sets that are larger than your memory. So to solve what I mentioned in the previous slide. But it's a very simple library. It's written in pure Python. But how does it obtain this goal to get parallel computing, efficient distributed computing in Python? Because it just uses the existing ecosystem. It doesn't do any computation itself. It will just build task graphs and based on blocked algorithms and schedule these graphs and try to do that efficiently. Now I had a little demo to quickly show you some things, but most of the things are also on my slide. So what is the idea? It provides some collections. For example, it provides Dask arrays, it tries to mirror the NumPy array interface, but under the hood, it's just a collection of many NumPy arrays who don't have to be in memory. So the Dask array is just, it will coordinate those collection of NumPy arrays. And if you, for example, you want to do a sum of a very big array that doesn't fit in your memory, or you want to do that parallel, this sum, it will read in all the different chunks, take a sum of each chunk and then combine those different sums. That's the idea of the blocked algorithms, and Dask knows about NumPy arrays and knows about how to how to make a task graph that can do such algorithms. But the actual computation still is just NumPy. Will still do the actual computation. But in that way, for example, the Dask arrays are used also with the X-array project. Typically, large climatic data sets, for example, the temperature of the full globe for several years. Typical array data that don't fit in your memory, but you can still do it on your own laptop. I can work on my own laptop with a very large data set because it doesn't read in all the data at once, and it can also use a different cores of my laptop to use them more efficiently. And it provides many functions that are available in NumPy will provide Dask as well. So you can, it's very familiar to use if you already know NumPy or know Pandas. The same for a Dask data frame. The same concept, but now instead of wrapping many arrays, it wraps many Pandas data frames. And again, in this way, you can work in parallel out of core with a very large data frame that doesn't fit in your memory, or where, for example, for more the distributed case, where your actual files or your actual data is, for example, distributed over different nodes of your cluster. Again, small syntax example. So instead of reading with Pandas, you do the read CSV from Dask data frame. What Dask does is all those operations, reading a bunch of CSV files, doing a group by operation, for example, taking the mean of a certain column. This is all lazily done. So it builds a task graph to do those computations, and it's only, and that's the difference. And so this is the difference with when using Pandas. It's only when you explicitly say, now I want to compute my results, that will the task graph that has been built up will execute it in parallel or distribute it on the cluster. So, for example, if you take a simple sum, the graph will not look that very not that complex. These are all your chunks, all your different arrays. It will read them in. It will take a sum, combine them. So typically, reduce them to smaller values. But you can also get much more complex graphs. For example, in this case, this is an example of using a matrix multiplication. For example, with a time series in Pandas, you can typically do a resample to convert, for example, from an hourly time series to, in this case, a weekly time series. So that is Dask. It knows those. It doesn't do any computation itself, as I said, but it knows what the resample is. It knows how to do that and how to translate this in a task graph. It knows that, for example, if I do a resample, that on the boundaries I will have to pass some data from the one chunk to the other to create the continuous time series. Another example, a rolling, so a moving average or moving window. If your data are divided in different chunks, each time the last part of a certain chunk will be have to be combined with the next chunk to have a continuous rolling operation. Of course, those collections work nicely if your problem, if the exact computation you want to do is an array or a data frame. That's not always the case. So it's also very flexible. You can create such task graphs yourself. It can be an arbitrary task graph. and it also provides some functionality to do that more easily. For example, here, yeah, it's a very simple example. You do some for loops, you call a certain function on some data, you stored it in a dictionary, and then at the end, you have another function that combines those results into a final output. If you want to do this in parallel, you want to distribute it, then the only thing you need to do with Dask is import the delayed function and wrap your function calls with this delayed function. By using this delayed, it won't execute directly when you run this code, but it will build up the corresponding task graph, and then you can let it, Dask compute it. So those collections, those Dask data frames, arrays, they create task graphs, and then we need to run those task graphs. So here you see an example. All the blue ones are done, and the red ones are either calculating or storing their results, because there is a future task that depends on them. So the task graph is very central in the Dask library. As I already said, you have arrays, data frames. You have also bags, which is more the where you can work with just Python lists or dictionaries, for example, if you have large JSON files to process, for example. The scheduler is then the part that will execute the task graph. There are a few schedulers built into Dask. Mainly here is which you can use just on a single laptop to work in different threads or to work in different processes. But you also have in an external library, the distributed library, a distributed scheduler. So, and that's the easy thing. You have different schedulers, but this part, the way how you interact with your code, how you write, work with arrays or data frames, is rather, it's almost exactly the same whether you work on your own laptop, for example, with multiple processes, or you work on a cluster with a lot of nodes spread over a cluster. So that makes it very easy to change the scheduler where you exactly run it, because you only have to, the initial scheduler, you have to change that. So the single machine scheduler, which is part of Dask, you can choose between multiple threads or processes by default. For working with arrays, it will use different processes, because NumPy and pandas can release the GIL for many operations. And this is a very small and stable library. The distributed one, where you just have your, you build a task graph on your own machine, but the scheduler can be on a remote cluster with many workers. So there, that's the distributed scheduler, and it tries to do optimize, because the data will be spread over the different workers, and tries to optimize that also the computations happen there where you have the computation that happen on those workers where the data are. It also provides some built-in into these projects some visual dashboards where you can see, for example, the different tasks that are executed over time, which is very easy to understand what is happening, but also to look into problems. For example, if you would see here a lot of white space, that means that there are no computations running, so we can diagnose certain problems. Those are also interactive graphs, so you can see what exactly is happening at certain points in time. So the red ones are the data communication. That's also, if you would see a lot of red, it's also a sign that something may be wrong. So to summarize, Dask is Dask scheduler. It's very familiar. If you already know NumPy and pandas, you can very easily start using it. It's very flexible. You can create custom graphs as well, or use the built-in collections. it scales up and scales down. You can, with almost the same code, run it on your own computer or run it on a cluster of thousands of cores. And it's also very useful for interactive computing. You can just, even when your computations are running on a large cluster, interact with it directly. And how does it do it? By building on the existing Python ecosystem. Just to finish, I want to thank, because a large part of the slides was based on slides of Matthew Rockling and Jim Christ, core developers of Dask, who are funded by Continuum Analytics, the providers of the Anaconda Python distribution. So that's it.
Thank you very much, Joris. Time for questions.
How does it compare to PySpark?
Yeah, so the question was, how does it compare to PySpark? I don't know exactly in performance, performance-wise or things like that, but the main thing is, of course, Spark is a very established technology. This is a much newer library. For me, the main advantage is it builds, uses the existing Python ecosystem, so it's also you're more in the C environment and not in the Java JVM-based environment, and that makes it more familiar for you don't have to switch between the two. Makes it more familiar if you're already using the existing Python ecosystem. So it tries to fill in the gap that exists in the Python ecosystem, that you don't have to switch to other ecosystems.
Great. I'm certainly will try.
Any more questions? Yes.
How easy it is to reason about the performance of the operations that you're doing with Dask? Is there, say, hard to parallelize it?
Yeah, the group bytes are rather, sorry. The question was how easy it is to reason about the performance for how to parallelize problems. The visualizations that are built in makes it a lot more easy to look at what is exactly happening. You can see which workers are where the bottlenecks. Many of the, certainly if you work with the data frames or arrays, then many of the group bytes and algorithms under the hoods are already optimized. They try to optimize, and it's a process going on. Also, the shuffles for sorting and joins they try to optimize it already. So many of those optimizations will be built in if you use the actual data frames and arrays. But of course, if you do more custom, make your own graphs, then I would say the visualizations, and you can always also directly access certain workers to interact with it to see if there is something wrong on a specific worker, etc.
There's another question.
Is there a preferred schedule?
Sorry.
When you're running Dask tasks for large clusters, is there generally a schedule
For the sorry, question. If you're running on a cluster, is there a specific scheduler? So for now, for the cluster, it's only one scheduler that they are developing, the distributed scheduler, which just creates a lot of workers and it communicates with all those workers. So it's only on your own laptop that you have some different options.
It's a new project. Is it already often used in production? Or?
So the question was, that's a new project, whether it's already used in production. I know that the Dask developers are, for certain parts, are working together with some companies in the US. I think Capital One is one of them that are using it and by their usage trying to optimize certain shuffles and joins and things like that. also in the, but I don't know if they're already use it in production. I think they are still developing within the company. Also in the X-array package, it's yeah, in the Python ecosystem, it's a bit a merger of pandas and NumPy. In the sense you have multi-dimensional arrays but with labels there, which is used with climatic data a lot. They also heavily use Dask to parallelize their
But you
workflows.
can foresee some hiccups.
Yeah, I think so. Yeah, I'm not very well positioned to evaluate that. There are certainly some things, for example, to set it up on a cluster. It's less integrated as other things. You will have to do some more manual things, but that tools to do that more easily are growing. So they're certainly less well integrated as, for example, Spark, which you can easily set up and things like that.
Time for one more question. I have one. Do you have any idea of the biggest scale that Dask is being used on in terms of number of cores or workers?
I know the Maturworking set it was used on a bit more than between 1,000 and 2,000 cores, and it should in principle. So they also he also said it on a blog post recently. It would much like that people try it out with larger things because it's very difficult as a developer to try it on such a large scale. But in principle, it should scale higher. The only limitation will be the scheduler, the time to the communication time of the core scheduler.
Okay, thank you very much, Yuri.